Today we're turning this breadboard version of the clock module and turning it into a fully fledged PCB design. There is a lot to cover in this episode, so let's get into it. Before I could even start designing my PCB, I first had to answer a very important question. What software should I use when there is so many to choose from? I did not have any previous experience designing PCBs, so like any reasonable person, I asked Google. After spending a bit of time reading recommendations and comparing different options, I eventually settled on KiCad as the software that I'm gonna use. Mainly because it's free, open source, has no limit on the project you're building, and it runs natively on my computer, which is a huge deal for me. It also has a huge community behind it, with tutorials, documentation, shared libraries, and plenty of people willing to help beginners like myself. I'm sure that community will come in handy later on. So let's start it up, shall we? KiCad isn't just one application. It includes a schematic editor, PCB editor, a footprint editor, symbol editor, a 3D viewer, manufacturing tools, and several other utilities. Before I had even drawn my first wire, it already felt like I was in over my head. But I'm not willing to let any software intimidate me. With KiCad finally open, it was time to start drawing the schematic. Finding components is actually fairly straightforward. You simply search the library for the parts that you need. And then, once you have assigned a footprint, you can go ahead and place it on the work area, and then start connecting everything together. The difficult part wasn't placing components. It was figuring out how to translate a working breadboard into a schematic for the very first time. Rather than trying to redraw the entire breadboard circuit from the get-go, I decided to start by recreating Ben Ether's clock schematic. Not because I wanted to copy his design forever, but because it let me learn how KiCad actually works without worrying whether or not I draw the circuit correctly. Instead, I could focus on learning the process one step at a time. How to find the components, how to connect them, how symbols and footprints worked, and how KiCad expects the schematics to be organized. After a while though, I felt confident enough to start replacing the copied sections of the circuit with my own designs. After all, the whole point of this project isn't to recreate someone else's computer, it's to build my own. So I started on one of the simplest circuits on the board, the RC debouncing circuit for the manual push button. One circuit became two became three, and before long the schematic started to grow surprisingly quickly. As more and more parts were added, I ran into a problem I hadn't really thought about before. The schematic was becoming a mess. Long wires stretching across the page, signals crossing over one another. Finding where a wire actually went became harder and harder with every new connection. At first I thought this was simply something you had to live with. Fortunately, it wasn't, because I discovered KiCad's global labels. Instead of physically drawing every wire across the schematic, I could simply give a signal I label with a name. anywhere else that same label appeared, KiCad would treat it as exactly the same electrical connection. And that made a huge difference. Instead of one giant circuit, I could divide the design into smaller blocks, like the trace clock, manual clock, run clock, the selection logic, and the power circuitry. Each block became much easier to understand on its own rather than interpreting the whole circuit at once. Another thing that I learned that would improve the readability of the schematic was assigning proper values and reference designators to each component. When you're adding dozens of components over several days, it's easy to forget why you are placing a particular resistor or capacitor and what role they play in the circuit. It is kind of like variables and function names in programming. If you give them nondescript names, it is really hard to remember what they are and what they are doing a week or so after. Likewise, giving every component its correct value and references makes the schematic much easier to read. Not only for someone else, but also for my future self. Eventually, after adding all of the different sections, the schematic was finally complete, or at least mostly complete. If you have followed this series, you'll probably notice that several things weren't part of the original prototype that I did. That is because moving to the PCB forced me to think about a few things that the breadboard prototyping let me get away with. The first addition that I made was to add decoupling capacitors to all of the ICs. This is one thing that I kept reading over and over again, that every logic chip should have at least one small 100 nanofarad capacitor placed close to its power pins. I'll be honest and say that I don't yet fully understand all of the details of the theory behind why they are so important. But when virtually every experienced electronics designer says, "Don't forget to add the decoupling capacitors," it seems wise to listen to them. Fortunately, 100 nanofarad ceramic capacitors aren't all that expensive. Also, when prototyping on the breadboard, I used this sort of power module that directly hook up to the breadboard. So I never had to deal with figuring out how to power the board. But for the PCB, I need to make my own power module. One of my original design goals was that the finished computer should be powered through USB. There are a lot of different USB connectors though, so how do I even choose one? So these are mini and micro USB cables. They were really common in just a few years ago, and all sorts of electronics had them. And I absolutely hate them. Always when I come across a device that uses these, I need to dig through my big pile of assorted cables to be able to use them. And most of the times, these cables doesn't really work that well. Probably because they have gotten full of dust and stuff over the years. Then we have this sort of cable. It's a USB-B type, and usually they are only reserved for printers. And for some reason, also my Arduino seems to have it. And look how bulky it is. I don't think I will be using this one either. So it is either going to be USB-A or USB-C. It seems like most of the new USB chargers that I buy have USB-C nowadays. So why should I go against the current? So to find an appropriate USB connector, I browsed DigiKey. After looking through what felt like hundreds of USB-C connectors, I settled on one designed purely for power delivery. That meant no tiny USB data pins to route, just the power connection and the two configuration pins I need to make the USB-C supply 5 volts. One thing I really appreciated was that DigiKey provides symbols and footprints for many, if not all, of their components. That meant that I could download the exact footprints for the connector that I was actually buying instead of trying to find the closest match in KiCad's library. While I was redesigning the power input, I also decided to add a few protection components. A fuse, a TVS diode, a proper power switch, and naturally a power LED, because every electronics project needs a power LED to indicate whether or not the board is actually powered or not. When it comes to the actual clock circuit, they changed very little from the paper schematics that I already designed. The trace clock, the manual clock, most of the changes here was simply about organizing everything cleanly using the global labels. One place where I did make some changes was the selection logic. Originally, I had used a 74LS00 quad NAND gate to build up AND gates for the control logic. However, I realized that I could instead use a 74LS08 quad AND gate, which would actually make the design more efficient. That also meant that I got 2 extra AND gates that I could do whatever I wanted with. And I decided to combine 2 of them to create a 3-input AND gate. That allowed me to gate the clock not only with the halting signal, but also with an additional program signal. I am not sure that I will actually use this additional control signal yet, but adding it was essentially free since we had these extra AND gates. But sometimes it's worth leaving yourself a little extra flexibility later on in a project. Another addition was this chip, the 74HCT244, a non-inverting buffer. The clock signal coming from the Schmidt trigger should already be nice and clean. What I wasn't so sure about was whether it could comfortably drive the clock signal across an entire backplane and eventually into dozens of different logic chips. Adding the buffer then gave me a much stronger output driver. Will it turn out to be necessary? Maybe, maybe not. But it felt buying myself some future insurance. Then there is this thing, a giant connector that dominates most of the schematic. At first, I thought I would use these pin header connectors to connect all of the modules to the backplane. However, I didn't really like the idea of having hundreds of these pin headers, since they could individually bend or break off. I just didn't know any better way to make these connections. Until one evening when I was playing my Nintendo 64, and I realized that the games themselves on these cartridges actually are just made from PCBs, and they don't use any pin headers to connect. Instead, they have pads on the PCB itself that make the connections, and it's really an elegant solution. And so I really wanted to incorporate that way of doing it. So once again, I browsed DigiKey to find these type of connectors. After spending far too much time comparing different connectors, I settled on a 2x31 edge connector. 62 connection may sound excessive, but one thing I have learned over the years is that resources that seem plentiful have a habit of disappearing much faster than you would ever expect. With more than 60 pins, labeling every connector individually would quickly become unreadable. Instead, KiCad lets you group related signals into buses. So I grouped the connectors into the 3 buses that I went over all the way back in the first episode: the data bus, the address bus, and the collection of control signals. The connectors also need to handle the powering of each individual modules. So I added 2 5-volt pins and 2 ground pins so that they can supply power to all of the modules. One final thing that you might have noticed with the schematic is that the switches and potentiometers aren't actually on the schematic itself. At least not directly. In the final design, I want those connectors to be able to be mounted separately on the case itself. And while I was browsing DigiKey for the edge connectors, I came across these IDC ribbon cable connectors. They seemed perfect for connecting a future front panel to the main PCB. The only exception is the main power switch. That gets its own large connector that's better suited for carrying the full supply current. Looking at the finished schematic now, it is hard to believe it started just as a prototype breadboard and a completely blank KiCad project. But the schematic was only half the challenge. Now I had to figure out how to turn it into an actual PCB. But first, let's just run the electrical rule checker, or ERC, that KiCad provides, just to be sure we did everything correctly. Oh boy, 14 errors and almost 500 warnings. That was far more than I was expecting. Although, to be fair, I wasn't really sure what to expect. But with some help from the KiCad community, I made pretty short work of the errors. Although dealing with those somehow seemed to make the warning situation even worse. One step forward and 2 steps back, I guess. Eventually, I did manage to clear all of those errors though. And as for the warnings, it turned out that a lot of them were actually related. One problem with the edge connectors were responsible for hundreds of warnings. So fixing those cleared huge chunks all at once. Some of the remaining warnings were simply caused by unused logic gates that I hadn't connected. I could have added them to the schematic just to satisfy the ERC, but that would have also made the schematic more cluttered. So instead, I decided those warnings were safe to exclude. But I made sure to document why. And before long, there were no errors or warnings left. The ERC should probably be seen as the first engineering review. It won't catch everything, but it can reveal many of the mistakes that inevitably creep into a complicated schematic. And now that this schematic is finally done, it's time to turn it into a PCB. So I opened the PCB editor and immediately I noticed that something was missing. None of the components from the schematic were there. No ICs, no resistors, no wires, nothing. It turns out KiCad doesn't automatically place the schematic onto the PCB. Instead, you first have to import, or rather update, the PCB from the schematic itself. Only then does KiCad generate all of the footprints and places them on the board. Or perhaps more accurately, it places them in one huge blob like this. At first I thought something had gone wrong though. Several of the components were still missing. After a fair amount of confusion, I eventually realized that those components simply didn't have footprints assigned to them yet. The schematic only describes the electrical circuits. The PCB editor needs to know what the physical part actually looks like in order to place it in the work area. So back to the schematic editor, I updated all of the missing footprints, and once those were assigned, the entire design with all of the components finally appeared. And then I got stuck again. On the breadboard, most of the placement choices were already made for me, since you can only place components in certain designated spots. On the PCB, however, every single component could go almost anywhere. That sounds like it would be wonderfully freeing until you realize that there are thousands of possible layouts for a board like this. I spent quite a while just dragging parts around without really making any progress. Not because the software were particularly difficult, but because I had absolutely no idea what a good PCB layout should even look like, and I had nothing to guide the placement of the components. Eventually I realized that I needed to stop searching for the perfect layout, and instead I needed to make myself some constraints. Ironically, adding constraints actually makes a lot of problems much easier to tackle. I figured that once I knew roughly how large the board should be, I could create a boundary that I could place the components inside. And that would dramatically decrease the amount of possible layouts. Rather than choosing a board size completely at random, I started with something familiar, a standard piece of perf board. The one I had available measured 160 by 100 millimeters. The height looked almost perfectly for the connectors that I wanted to use. And the width, well, not so much. Estimating the space that the edge connectors would take up revealed that they would roughly cover the 160 by 100 millimeters all by themselves, or everything would be very cramped together. Adding another 40 millimeters gave me enough room for both the connectors and the clock circuitry without making the board unnecessarily large. So I settled on the 200 by 100 millimeter form factor for the board. Estimating the board size this way had another benefit. It forced me to start thinking about how the finished board would actually exist in the real world. Where would the connectors go? Where would the switches connect? How much room would I need for the cables? The PCB was slowly changing from an abstract drawing into something I could actually imagine holding in the physical world. So once I had drawn the outer border of the PCB, I actually already knew roughly where I would place the different components. Before starting this project, I thought routing would be the difficult part. However, component placement turned out to be where almost all of the thinking happened. The larger components were easy enough since their placement were given by the constraints that I had set out. For the remaining circuitry, I kept each functional block roughly together, just as I had when organizing the schematic. The only real exception was the decoupling capacitors. Those belonged next to their power pins for each of their respective IC rather than grouped together. After that came a lot of moving to get everything in a good position. Rotating, moving again, rotating again, trying to both figure out where each component should go, while also minimizing all of those crossing connection lines. One thing that surprised me was how useful the global labels actually became for the PCB layout. Because this schematic wasn't tied together with long wires, I could easily reorganize the signals, swap equivalent logic gates, and simplify the routing without having to redraw half of the schematic, just by moving around the global labels. It was just another reminder that the schematic directly influences how easy or hard the PCB design become. Looking back, I spent way more time placing the different components onto the PCB compared to any other step in this process. However, once they were placed, routing the different components were strangely relaxing, and I could just lean back, put on some headphones with an audiobook, and the traces were drawing themselves.
Call me Ishmael. Some years ago, never mind how long precisely,
Since most of the difficult decisions had already been made during the component placement. Well, most of them. Naturally, the last few traces refused to cooperate. Those still required quite a bit of thought before everything finally fit together. Instead of routing individual ground traces all across the board, I let KiCad fill the unused copper with a ground plane. Besides saving quite a bit of routing, it also provides a much better common ground connection to the entire circuit. At least once I remembered to actually connect the copper pore to the ground net. With all of that done, just like the schematic had ERC, the PCB has DRC, the design rule checker. Instead of checking the electrical logic, DRC checks the physical design. Are traces too close together? Are pads overlapping? Is the board outline valid? Those sort of things. Fortunately, there were nowhere near as many problems this time around. That doesn't mean there weren't any though. But just like before, I simply worked through them one at a time. With all of the errors gone, I cleaned up the Silkscreen, moved a few labels to the right position, made sure that everything was readable, and at that point, I finally started feeling that the project was on the final stretch now. There was just one thing missing. It looked like a PCB. but I wanted it to look like my PCB. Therefore, I decided to add my logo to the board. Fortunately, KiCad has a surprisingly handy image converter that with just a few clicks lets you import an image and convert it into a Silkscreen object. It isn't electrically important or anything, but somehow that tiny logo made the whole board feel like a finished product for me. It's funny how small things like that can be so important in a project like this. At this point, I was feeling pretty pleased with myself. The components were routed and all of the errors were handled. And all that seemed to remain was to manufacture the board itself. However, that was when a pretty inconvenient thought occurred to me. How am I supposed to test the edge connector? Surely not with one of these perf boards. So I decided to build another module, one with edge fingers attached to them. The design process was almost identical, so I won't go into it in detail. The interesting part of this was the construction of my very first custom footprint for the edge finger connector. KiCad also includes this dedicated footprint editor for exactly this sort of thing. Using the mechanical drawing from the connector datasheet and double-checking the real connector with a pair of calipers, I laid out the first pad. The rest were mostly a matter of duplicating the pad and then space them out according to the datasheet. Once all of the pads were complete, it was just a matter of adding the board outline, the courtyard, and then finally we should have a footprint that hopefully fits the real connector. I'll admit, creating a footprint from scratch sounded terrifying when I first started, since you need to be so accurate in all of the dimensions in order for it to actually work in the real world. But at this point, it was just another problem that could be solved one step at a time. Now that the two boards are finally finished, it's time to send them off to be manufactured. The two manufacturers that I know of is JLC PCB and PCB Way. I will let you figure out how I knew of those two. But how do I choose between them? I'll be honest, I wasn't really in a position to compare manufacturing tolerances or production capabilities. So I made my decision the only way I know how. Who has the best deals? JLC PCB offers your first set of PCBs for only $2. Honestly, I've spent more than that on a cup of coffee. So, JLC PCB it is. That amazing deal didn't actually apply to either of my boards though. The clock modules was larger than the 100 by 100 millimeters. Since the test board uses edge fingers, I choose the Enig finish instead of standard hassle. I am not sure if that's entirely necessary, but if you have any experience with this, let me know in the comments below. With all of the other settings taken care of, there was still one critically important engineering decision left: the PCB solder mask color. Now, JLC PCB offers all sorts of colors: black, blue, red, white, and even purple. But I had already decided to make my TTL computer as retro as possible, so there was really only one choice. I guess now all we can do is wait. I wonder who that could be. Now that's what I call express delivery. Each board module came individually wrapped in thick bubble wrap inside of a sturdy box. It definitely gave me confidence that they would have survived the long trip from China. I have watched countless videos where creators received prototype boards in the mail. I never really imagined I'd be opening a box containing boards that I had designed. And here they are, my very first two PCBs. They look incredible and I'm so happy. It's almost like a professional made them. So let's have a closer look, shall we? That is unfortunately all that we have time for today. In the next episode, we are gonna populate this board and see if it actually works. So subscribe so that you don't miss that episode. Bye!